So in this video, we'll see how to use small ripple approximation and switching cycle average of a converter. So the topic of the discussion would be small ripple approximation SRA and switching cycle averaging technique. Whenever we design a converter, we keep in mind that the output voltage, in case of DC-DC converter, we give in some input voltage and we try to get some output voltage V of t such that Vg and V of t. Vg is usually a constant voltage, but we will see that there are cases when Vg can also vary, but we still want to maintain V of t is equal to constant. This is the case of a DC-DC converter. Here we place in the switching elements and the filter elements. So let me draw it properly. Yeah. So here we place in the switching and the filtering elements. So this is what a converter looks like. So I'm writing this V of t as constant, but it is not a constant, since we have seen when the diode voltage across the chopper varies like this, the output voltage V of t varies like this, right? So what I'm talking about is a chopper in which we have a switch and a diode and an inductor and a resistor. This is the simplest configuration. So in this, the diode voltage is varying and the output voltage is also varying, but we can see that there is a DC value for this output voltage. So if I just separate out the output voltage, I have something like this. If I represent it, this is a DC voltage V plus some small ripple. This exact equation, this exact waveform in red color, we obtained it from solving a differential equation, right? What if we ignore this part and say output voltage V of t is approximately equal to V? Even this is the case for a well-designed converter. When we design a converter, we hope or we try to design our ripple voltage should be less than, let us say, 5% of the total voltage. So in that case, we can approximate V of t with a constant voltage. Then this affects how we solve our differential equations. We can simplify our analysis to a greater extent and obtain at the same result that we have tried to derive from a long solving procedure of differential equation. Right, we have in the previous videos we have derived that the output voltage is equal to Vg into duty ratio. Since we are in steady state, I'll use the capital D's as the variables. So this we have arrived after applying first order Taylor series approximation to the equations. But now with small ripple approximation, we ignore the ripple content and we try to arrive at the same equation with less effort. And The points that I want to mention are when we can apply, where we can apply small ripple approximation and where we cannot. So first of all, it should be applied to continuous waveforms. Continuous waveforms, which includes inductor current IL and capacitor current VC. Capacitor voltage VC. So we should not try to apply this small ripple approximation to discontinuous waveforms just like the voltage across VD. We should not apply small ripple approximation to switching voltages, which is discontinuous, right? This is a discontinuous waveform. Whereas the nature of inductor current and capacitor voltages are continuous in nature. So let us try to use this and try to derive our chopper equations. So we have already seen that when the switch is turned on, we have this sort of circuit, and we have also emphasized that the time constant of this particular current, let us say if we solve this circuit, the current reaches a final value equal to Vg by R, right? But the time constant, let me draw it better. Yeah, so the time constant is somewhere of this nature, right? And the switching cycle is of this order. So we can see that in that region we can approximate the nature of the curve with a straight line. So in this region I can approximate the nature of the inductor current and the nature of the resistive voltage drop with a linear curve. So now this is the case 1 in which using small ripple approximation we are saying this voltage is equal to some voltage V. So then we have our inductor voltage across inductor to be VL is equal to Vg minus capital V. And similarly, when the switch is turned off and the diode is turned on, then we can write our equation as zero is equal to VL plus V, right? So from this we can write VL is equal to minus V. Now we try to introduce the fact that under steady state we have seen that the current IL of t is equal to IL of t plus Ts, right? We have seen under steady state this value should be equal to this value, right? So if we extend that idea further, we can say that integral DIL, or we'll just try to write the voltage equation across inductor VL is equal to L di by dt. So if we try to integrate this voltage within the intervals t and t plus ts, then we end up in d, and we are integrating the limits under t, IL of t and IL of t plus ts. So what do we end up with? So from this we can say that IL of t minus IL of t plus Ts is equal to 0, that is equal to 1 by L integral t to t plus Ts into VL of t dt. From this we can arrive at the fact that average, I'm using a symbol for this particular integral, inductor voltage averaged over period Ts is equal to 0, right? So let's use that information and try to use these equations. So from the small ripple approximation, what we are trying to do is the inductor voltage is as follows. When it is turned on, we are saying it is Vg minus capital V. When it is turned off, it is minus V, right? And this is turned on for T on, and this is turned off for T off. So if we represent it in duty ratio, then Vg minus V, and try to find out and try to average this out over this time period, then see what happens, into capital D into Ts, which is turn on time, plus minus V into 1 minus D into Ts. So Ts will go away, and Vg into D minus V is equal to 0. So V is equal to Vg into T. The same equation we have arrived at. Like we derived a complicated equation in terms of exponentials, and then we substituted Taylor series approximation. Then we arrived to this position, to this equation in the previous tutorial. Right now we have used small ripple approximation. Similarly, we can find out the inductor ripple as well from the following equation. So the beauty here is, as we said, when you are in under the time scale of a switching time period, the inductor voltage is just a linear slope that we have seen. Actually, the slope should be following an exponential curve. Since we are in the time scale of switching period, which is far less than the time constant of the circuit, we are approximating the slope of the circuit as this under turn on condition. This slope is valid till 0 less than t less than dts. So if we try to write down this, then we know that we can replace Vg as t into Vg, right, by L, that is equal to Vg into 1 minus d by L. We have replaced the capital voltage, capital V, with this equation. Then we are at this, and this particular change is, I am representing it as 2 delta IL divided by what is the change in time from 0 to dts. So this is dts. So from this we can calculate delta IL. Delta IL is equal to Vg into 1 minus d by L into d by 2. And we also know what is our average inductor current, right? Average inductor current is nothing but average output voltage divided by R, which is nothing but d into Vg by R. So we take the ratio of both of them, we get delta IL by average inductor current, which is equal to the load current in this case, in this chopper case. So we end up in 1 minus d into RTS by 2L. So the analysis has been simplified using switching, cycle, averaging, and small ripple approximation. Please note that small ripple approximation is valid for only continuous waveforms under the assumption that the switching time period is far less than the time constant of the circuit. Right? Thank you.